Good afternoon, everyone. Today we are very happy to have Felix Haehl from IAS to tell us about the spin classes and holography. So please take it away, Felix.
So thank you very much for the invitation. It's nice to talk to all of you. So I'll tell you about mostly about the second paper, the more recent one with Maine Christos and Subir Sachdev from Harvard. And I'll also mention, if I have time in the end, I'll also talk about the earlier paper with Tarek from Amsterdam on a different model of spin glasses, and the motivation will be to understand some of that physics in the context of ADS-CFT, connected to some of the other things the community is thinking about. So here is kind of the big picture, that in many of these recent discussions about ADS-CFT, disorder and averaging over ensembles or various other notions of averaging have played a crucial role in many of the insights that people have come to. So for example, we have learned that sometimes semi-classical gravity seems to describe averaged quantities. The paradigm being JT gravity, which describes the low energy dynamics of SYK type ensembles, and then various generalizations of these ideas and different notions of averaging over other ensembles, other theories, or microcanonical windows, or time, or all sorts of things, which are then in turn related to interesting quantities in gravity, such as space-time wormholes, gravitational instantons, and so on. So it's very desirable to understand other characteristic properties of such disordered systems and what they mean for understanding of ADS-CFT. So I'll talk a little bit, okay, I'll review a few things that are hopefully known to most of you, and then I'll talk about this random Heisenberg model that we studied recently. Then I'll speculate a little bit about the holographic context, and if I still have time, I'll mention a different model, which is the one we studied in the summer with Tarek, and which has some other interesting features. Okay, so let me start from the beginning. So this whole all these recent developments in ADS-CFT have started with the SYK model, which is this model of Majorana fermions, where you have random disordered couplings from some Gaussian ensemble, and which is very useful because it's solvable at large n and a strong coupling. The way this is done is by formulating a mean field description of the theory at large n in terms of a bilocal field, a bilocal two-point function, and the corresponding self-energy field. Now, a way to think about much of the physics is in terms of an emergent reparametrization symmetry at large n, or at strong coupling, which is spontaneously broken by the saddle point solution, and it's also explicitly broken. So the time reparametrizations around the saddle point are not quite a symmetry, but they become soft modes and acquire a small action. And this famous Schwarzian action, which describes various leading effects in gravity and in this strongly coupled system. The Schwarzian degree of freedom, this reparametrization, is associated with the boundary degree of freedom associated of dilaton gravity in ADS2. And of course, a complete holographic and microscopic understanding of the whole model is still missing, but many of the features at low energies are described by this JT gravity. For example, the non-standard thermodynamics, so for example, I'm giving here the entropy, which to leading order has some term S naught, which is topological from the point of view of gravity, but then there's an interesting leading correction, which is linear in temperature and extensive in n. And that correction to the entropy would be described by the Schwarzian, for example. So these Schwarzian effects are enhanced at low temperatures. Another example for this is quantum chaos, as quantified by these out-of-time order correlation functions. I will, if I get to it, I will explain a little bit more what that is in the background. But most of you have probably seen these out-of-time order correlation functions, which at whose connected piece at order 1/n describes exponential growth with some Lyapunov exponent, and the leading contribution to this Lyapunov exponent at large beta j is again described by the Schwarzian degree of freedom. So a lot of the interesting physics is encoded in that. Now, what are spin classes? So this is what this talk is going to be about. Is the fact that many of these disordered systems, they exhibit a different phase of matter at low temperatures. And sort of the intuitive reason for that is that because of the randomness in the couplings, so all the models I'll talk about have these random Gaussian couplings, which introduce interactions between all the degrees of freedom, all-to-all interactions. And the fact that you have these all-to-all couplings leads to a very complicated free energy landscape, and ultimately to frustration, because each spin feels forces from every other spin. So it's not clear in which direction it wants to point. And the free energy landscape that results from this is very complicated and rugged. So the simplest example, simplest classical example for this is this Sharington Kirkpatrick model, which just involves these kind of Ising spins and two-prong interactions which are random. Now, if you study this model, then you'll find that as you lower the temperature, the dynamics of the model slows down over orders of magnitude, and it becomes very viscous, and the relaxation times diverge. And ultimately, these spin degrees of freedom, they freeze in some state that's locally stable, but it's not the global minimum of this complicated free energy landscape. But the system freezes in one of these states and loses ergodicity. So the accessible states become uncorrelated, and you're stuck in one of these minima, roughly speaking. So obviously this is a very complicated problem. So we need a useful mean field sort of way to describe what's going on. And a useful order parameter is this Edwards-Anderson order parameter that will show up in various places, which is sort of the averaged square of the magnetizations. So you might think that you can just consider the one-point functions of these spins, the expectation values of the local magnetizations, and average those over this order. That's the overbar. But that would just give you 0 at any temperature, because these spins get stuck in some random direction. So after you disorder average with some unbiased disorder, you would just get 0, but you can get something non-trivial if you square them before you average. So one way that this arises is from two-point functions. If you consider spin two-point functions in the long time limit, we will encounter this order parameter. So one of the signatures of this glass phase will be that the long time limit of two-point functions after you average over the disorder has a non-zero value. So whenever this order parameter is non-zero, that will signal that we're in this phase. Okay, so the goals for this talk will be to characterize some of the features of these classes. So some of them I already mentioned, that there's a large landscape of these metastable states, and we have to find a useful way to think about that. And about the dynamical properties, which slow down, and eventually the two-point function doesn't decay to 0 at all anymore. It just decays to this order parameter. So the system can't quite reach thermodynamic equilibrium, but it can't do so in a very particular way that one can understand in an interesting way. So we want to understand some of these properties, and then with ADS-CFT in mind, ask some of the questions related to the points that I had in my review section. What happens to the 0 temperature entropy? What happens to this emergent reparametrization symmetry and the Schwarzian and all that? We can also think about quantities like the Lyapunov exponent and ask about what happens to that at low temperatures in such classes. And then at the end of the day, we would like to understand within this holographic paradigm, how do you think about these properties? Okay, is that clear so far? Okay, so I'll talk. Okay, I already mentioned this Sharington Kirkpatrick model. One way to think about the two models that I'm going to discuss is as quantum generalizations of that, very roughly speaking. So I'll start talking about this random Heisenberg model with SUM spins. So we basically consider the Sharington Kirkpatrick model, where we replace the spins by SUM spin operators. So the physically interesting case, and the most familiar one, is for SU2. When these are SU2 spins for n equals 2, then these S alpha beta, that's just the spinor notation for for SU2 spins. So you could think of Pauli matrices. I'll be a little bit more specific on the next slide. So as we'll see, this model is very closely related to the physics of the SYK model, the complex SYK model. But in addition to that, there's this parameter M, and we will consider the large M limit. And we'll see that for the finite M corrections give you spin glass order in this model that we can understand analytically. And then in the last section of my talk, I will mention this p-spin model, where we consider, instead of these ±1 spins, we consider bosonic rotor degrees of freedom, sigma I, which parameterize a sigma model. So these sigma I lie on a high dimensional sphere. They satisfy this spherical constraint, which is just another way of saying that these describe that this is a sigma model with a spherical target space and random couplings. And this model is nicely motivated by some higher dimensional constructions in string theory, which I'll mention briefly. Okay, so let me discuss now this random Heisenberg magnet. So as I said, we have these, we consider these random Gaussian couplings. This should be a J, so they couple SUM spins on side I and J. And I'm gonna, I have to choose a representation for these SUM generators. So I'm considering a fermionic representation where you can think of these SUM spins as being written in terms of fermions F and F dagger. So in the case of M equals 2, just have in mind Pauli matrices for these guys, and they have to satisfy a constraint. So F dagger F, if you sum over all of them, they have to satisfy a constraint. So again, for the case M equals 2, this means there would be two fermion, two possible states on each side. But because of the constraint, you can only have one at each time. Okay, but we'll generalize this M equals 2 case and consider SUM spins here. Now, if we choose this representation in terms of these fermionic spin-on degrees of freedom, I'll refer to these Fs as the spin-ons, we introduce a U1 gauge invariance, as you can just see from writing it in this way. So much of the physics that I will describe can be understood in terms of what happens to this U1 gauge invariance. But okay, let's start the pedestrian way. So what do you do with this kind of model? Well, the first thing we want to do is understand something about the thermodynamics. So we want to compute the free energy and then the entropy and see what happens to such quantities. So when we compute the free energy, so log Z, we have to disorder average with this Gaussian weight. But we have to disorder average after we take log Z. So it's important, if we want to do this properly, to compute the quenched free energy. And the partition function Z is just, the Hamiltonian I described. That depends on these two parameters, N and M, the number of sites and the M from the SUM. And then we'll put a kinetic term for these fermionic spin-ons. So it's a one derivative kinetic term. And we introduce a Lagrange multiplier lambda, which implements the constraint we had here. Good. now, okay, so back to computing the disorder average of log z. So the way we do this is, of course, by using the replica trick. So we write log z as the limit of powers of z, integer powers little n, and then compute the free energy as the limit of that as n goes to 0. So now we face a simpler task, which is just computing the disorder average of z to the n. And to compute that, so z to the n just means we have now n copies of the system. So all these degrees of freedom, the fermions and the Lagrange multiplier, they now get a replica index a that runs from 1 to n. In the end, we take n to 0. Okay, so now we want to disorder average z to the n. The way we do this is very similar to the way we do it in SYK for those of you who have gone through these calculations. So we introduce a collective degree of like a G field, a fermion bilocal, which is just the sum of all these spin-ons F dagger. So that's going to be the fermion 2-point function. And we're going to need other collective degrees of freedom. So there's going to be a sigma field, which is the Lagrange multiplier that implements this constraint. And then there's going to be a Hubbard-Stratonovich field Q in addition to G and sigma. So what this Q does, it decouples the quartic interactions. So if we write the Hamiltonian is quadratic in S, but if we write these S in this fermionic representation, then it's going to be quartic in F. Okay, similar to the SYK case. And to decouple these quartic interactions, we're going to introduce a Hubbard-Stratonovich field, Q. And so after you do that, you introduce in the path integral for z to the n these three fields. Then you can integrate out both the disorder, the couplings Jij, and the fermions F. And after you do that, you get a path integral that only depends on GQ and sigma. Well, and the Lagrange multiplier. Okay, so I'm skipping some of these steps, but what I've done now in my mind is integrate out the couplings and the fermions, and then the resulting path integral for GQ sigma, we evaluate for large n. We do the large n saddle point. Okay, so we get an effective action at large n, and I will not consider any one over n corrections. So as far as n is concerned, this is the problem I'll consider. There's an effective large n action, which involves Q, and then an auxiliary problem that involves log of some auxiliary partition function ZF, for which Q is an input. So this ZF is kind of what's left of the path integral over G and sigma with replica indices, and with the saddle point value of Q as an input. Now this auxiliary problem, so there's still a path integral to do. You see that this action comes with an m up front. So after we take the large n limit, there's still a non-trivial problem here which involves an m up front. And the action that appears in this G sigma path integral looks very similar to the one that might be familiar from SYK. So it involves this logarithmic determinant that has the kinetic term in it and the Lagrange multiplier in this case, and this self energy, and then some interaction terms here.
Excuse me, could you comment on the gauge invariance of this way of doing things?
Yeah, so this expression here is gauge invariant. So I wrote here how the F degrees of freedom transform, and from this you inherit the gauge transformation for all the other fields. So for instance, it's obvious how this G transforms. It picks up two phases, tau and tau prime, and the similar transformations for sigma and Q, and lambda essentially transforms like the gauge field. And then this whole expression is gauge invariant.
Thank you.
Yeah. All right. So this is the large n problem, which is still exact in M from SUM. The large n saddle point equation that you get from up here just tells you that Q is essentially the 4-point function of fermions, or the 2-point function of G, with respect to this partition function ZF, so that this auxiliary problem described by the action I. Okay, so what we're going to do next is we're going to consider the large M limit on top of this. Because for large M, we can saddle point this integral and solve this auxiliary problem. All right, so I'll discuss the saddle point problem for large M here to solve this path integral. And then I will discuss fluctuations. So we will consider 1 over M corrections to this problem. Okay. Are you still following? It looks a little bit complicated. But
Yes, it's a bit complicated, but just let me ask, it seems like you have already this 1 over M leading contribution, this correction already in this QAB. Where did this come from? In the last equation that you have 1 over M corrections already, right?
Oh, this is just, so this is still exact in M. The first term here just comes from, from here. So if you, so this down here is just a large N saddle point equation, but I have not assumed a large M yet. So you could do this for M equals 2.
Okay.
So this first term here is just, it's not very important. It just comes from the normalization condition.
So when in the large M, this goes away.
Well, in the large M limit, this is going to be a
subleading.
M. Yeah.
Okay, thanks.
But the interesting problem will be to solve this G sigma path integral in the large M limit. Okay, so here's something that looks hopefully familiar. So if we now consider on top of this large N, we consider large M, and we saddle point in both of these parameters, then the equations of motion we get are just these. So these are just the saddle point equations where we take large N first and then large M. These are saddle point equations for G, Q, and sigma. And they have replica indices A and B still. But so remember that GAB was the 2-point function for the fermions, for these spin-ons F. And so they cannot have replica off-diagonal correlations, because that would factorize and you would get 1-point functions of these spin-ons, and that's 0. So these G's, the G has to be replica diagonal in these AB indices. But if that is replica diagonal, then you see that everything in these equations has to be replica diagonal. So these large M saddle point equations are only equations for, they impose replica diagonal solutions. So I can drop the replica indices, and then the equations take this form in the middle here. Okay, so these are now the saddle point equations at large M along the replica diagonal components. And these are precisely the equations of the complex SYK model. So, this set of self-consistent equations for G and sigma, I have already plugged in the value of Q here, so that the self-energy is GQ. Right, so these blue equations here, that's exactly like in the SYK model. The difference now is that, G is a 2-point function for these fractionalized degrees of freedom, these spin-ons that I introduced to formulate the problem. But other than that, at the level of the equations, these are precisely like for complex SYK. So the large M limit of this theory has these well-known equations that have been studied since the Sachdev paper, and of course in recent years in the context of holography, and they have all the properties that we're interested in. With emergent reparametrization symmetry and connections to gravity and so on. So that's what happens at infinite M. And now we want to understand 1 over M corrections.
Can I ask a question?
Yeah.
Well, the thing is that so you have a model where you have randomized disorder in terms of these couplings, and you have replica symmetry. So it's not so surprising that you would end up with something which resembles SYK in the end, is it?
No, I mean, yeah.
I know. I mean, your work is really nice. That's definitely, not the point I'm trying to make.
Yeah, that's not. I mean, it's also not new. This was, this was understood by Sachdev and Ye in '93. Right.
So, I mean, wouldn't like all such models belong to the same universality class or something like that? Is it possible to make such a statement?
Well,
wherever you yeah.
I mean, what I've discussed so far is the large M limit. Now, as we'll see in a second, once we consider finite M corrections, something quite different is going to happen.
Okay, great. All right,
yeah.
Thanks.
So that's going to be the next thing. So this was the saddle point at large M, and I will now discuss what happens if you consider one over M corrections to this G sigma path integral. And that will introduce this spin glass physics and very different properties. Okay, so let me first discuss it like at the level of phenomenology or numerics, and then we'll get some analytic understanding of what's going on. So to characterize what's happening at finite M, one thing you can do is consider the spectral function, which is defined up here. So Q, recall Q was the 2-point function of G, so it's like a 4-point function of the fermions, and we consider it's a spectral representation. Now you can, I mean, one thing you can do is solve this problem numerically. So this was done also a long time ago, or it was done more properly again recently. Well, okay. So what's the properties of this spectrum? So at large frequencies, we have the SYK behavior. So this is linear in omega. That's this dotted line essentially. Yeah. So if this linear in omega behavior, which you can think of as the gravitational contribution, it's the piece that comes from the Schwarzian action, and it's subleading to the piece that just goes like the sine of omega that describes the conformal, the long time behavior. So in position space, that's the property that Q goes like has this scaling form. So there's this conformal piece, and the first correction is the Schwarzian piece, and then there's other corrections which are understood to a lot of, in some detail in this paper. So that's the physics at infinite M. Now, if you solve the problem numerically at finite M, so for instance, for M equals 2, which is the physically most interesting case, then you see that the low frequency spectrum gets quenched, and these low energy degrees of this low energy density of states, and therefore the spin fluctuations, they get suppressed. So the extensive number of low energy fluctuations that we had, they sort of accumulate into a delta function. So they all go to zero frequency, and the spectral function goes to zero linear in omega. So we have this linear in omega behavior, both at higher frequencies and at low frequencies, but the spectral function goes to zero. So what does this delta function mean? If you translate back to the time domain, according to this definition up here, the delta function just means that Q of tau has a constant piece, right? So Q of tau is a constant plus some tau dependent contribution. And this constant piece is precisely related to this Edwards-Anderson order parameter that I introduced in the beginning, which said that we can diagnose spin glass order by a constant behavior in the 2-point function at long times, at low frequencies. Okay, so this kind of spectrum is what we want to understand. and we can understand it analytically in this model in a perturbation theory for large M. Now, okay, so time. So much of this, much of what's going on here, you can think of in terms of this U1 gauge symmetry. So this won't play much of a role, but let me mention it as an aside. So the SYK spin liquid is a gapless system with these spin-on excitations, these fractionalized excitations, and the U1 charge, the U1 gauge charge is carried by quark-like degrees of freedom. So these spin-ons are kind of like quarks. It's sort of the high frequency part of this spectrum. And then at finite M, you see this behavior at small frequencies, which is like a confined phase for this U1. Okay, but let me sharpen a little bit the thermodynamic properties or consequences of this spectrum. So another way to think about this is in terms of the entropy, right? So because this density of states here is suppressed, this also means that the thermodynamic entropy disappears. So it seems like the entropy in this state is going to go to zero at zero temperature. So here's a sketch of what we would expect this entropy to look like. Again, at high temperatures, it has this behavior that's as in SYK with some particular constant contribution, and then this correction that's described by the Schwarzian and so on. But now what corresponds to this kind of spectrum is the fact that the entropy will drop to zero as you lower the temperature. The entropy will not go to a finite value. So this sharpens the question that I want to ask, which is how can this be? How can the entropy vanish despite there being this huge number of metastable states? Like in this picture I had in the beginning. So we want to understand that. Okay, so let me now describe a little bit how we can think about this.
I want to ask a question about how do you distinguish between the spin liquid phase and the spin glass phase, or just by you just see this whether the entropy can go to zero when you take T to zero?
Yeah, so one very convenient way to distinguish them is what's the value of the Edwards-Anderson order parameter, or a more detailed version of that question is to ask what does this spectrum look like. So the SYK spin liquid has this spectrum with gapless excitations, and the spectral function approaches a finite value at zero frequency. Whereas in the spin glass, corresponding to this finite M model, you have this behavior, which is quite different, and this delta function in particular corresponds to the Edwards-Anderson order. So that's one way to distinguish them, by computing this spectrum, which is just the same as computing the two-point function. Mm-hmm. So you can, here in the top right corner, those were the equations, well, the large M equations. Of course, okay. you should consider the finite M equations, and you can just solve them numerically, for example, and ask what are the properties of these two-point functions.
Okay, so the difference is really in the low energy spectrum part.
Yeah,
I mean the difference.
That's where you see the sharpest difference. Yeah.
Okay.
Okay, so now let's do one of M perturbation theory. So if M is finite, then these G, sigma, and Q variables, they need not be replica diagonal anymore. So we're not going to make a simple ansatz, or well, it's basically just notation. We're going to say that this Haber-Stefanovic Q, which is like the 4-point function of the fermions, has a replica diagonal piece, which could now have a constant in it. That's part of the spin glass order, if that constant is non-zero. And then we allow for some matrix of off-diagonal constants. if these are non-zero, that will signal spin glass order. And now with this ansatz for Q, we can solve the large M problem perturbatively. And basically, we're going to work perturbatively in this Qs. So in this constant matrix that describes the spin glass order and the replica off diagonal correlations, so the overlap between different replicas. Okay. Now, the thing we set up to compute was the free energy, log Z, this order averaged, sorry. So we can compute that just order by order in 1/m. Okay, so we had this G sigma path integral, which had an auxiliary action with an M up front. And we can compute that by saddle point and then compute the one loop determinant and various fluctuations to get the free energy to any accuracy we want. And what you get is some Landau type free energy functional, where you essentially produce all possible terms that you could imagine. So perturbatively in powers of these Q parameters, you produce pretty much anything you could get with various coefficients that we can compute in terms of diagrams. So these coefficients have some value, but it's not going to be too important. What I want to mention is that some of these terms are going to have an explicit dependence of beta, or even beta squared, and so on. So it seems that some of these terms are divergent as we send beta to infinity, go to zero temperature. Okay, so I only wrote out the betas here, which are explicit betas that give you divergences at zero temperature. So that's not good, right? So the free energy better be finite, otherwise the model doesn't make sense. So what we have to ask is whether there are values for these Q matrices for which this free energy is consistent. And indeed that exists. So we can just extremise with respect to these parameters, and then we'll find values for those such that all these dangerous terms in blue vanish, so that the free energy is indeed finite at zero temperature. What does that solution for these spin glass order parameters look like? At zero temperature, it's very simple. It's just all of them have the same constant value. That's again this order parameter, Edwards-Anderson order parameter. At finite temperature, it's a little bit more complicated. So then this QAB matrix has a particular structure that was discovered by Parisi. And this structure is precisely engineered such that or has the property that all these dangerous terms vanish. So the structure, I can describe it briefly. So this QAB matrix, first we consider this to be a very large matrix. So we have many, many replicas, and we want to describe an ansatz that will allow for analytic continuation for as n goes to zero. So little n, the number of replicas. Okay, so we need an ansatz for which this can be done. And the ansatz that solves the problem has the structure that you have blocks along the diagonal, and everything else is one particular constant. And then these blocks have again a block structure that they're composed of blocks along the diagonal, and everything else is a constant, and so on. You keep doing this for infinitely large matrices, and then you take the limit n goes to zero, so you make the matrices small. Okay, so this is just the usual quirks of the replica tree. But so what you find is something very nice. So in the limit, as you take n to zero, so first you make these matrices huge, and then you collapse them. And in that limit, this QAB matrix can be described in terms of a function Q of x on the interval 0 to 1. Okay, so there's a continuum limit in some sense, where this whole matrix structure is just described by a function, and the function that solves the problem is piecewise. Well, it's continuous, and it's piecewise linear and then constant. Okay, so this is the function you find. Right. So at the end of the day, this whole complicated structure with all these blocks and so on is described in terms of this function, which is characterized by only two numbers. the Edwards-Anderson order parameter, which is the the value where the function saturates, and a breakpoint parameter m, little m, that tells you at what point between 0 and 1 the function changes its behavior. And this parameter m, so we've already seen the Edwards-Anderson order parameter in many contexts now, and we have seen that this is physical. This is a long time limit of 2-point functions. This m here is also kind of physical, as we'll see in a second, or at least it will be useful to treat it like a thermodynamic quantity, similar to the temperature. Okay, so this breakpoint parameter, which is a property of the replica of symmetry of breaking ansatz, is going to characterize the thermodynamic state. And we're going to use this m now to define a quantity. It's called complexity in the spin glass literature, which is going to answer the question, what happens to the entropy? Okay, so yeah, let's maybe first recall how you do this, how you do the usual thermodynamics at the bottom here. So if you do the usual thermodynamics, you have an on-shell action which you identify with the free energy F, and then you can define, in particular, the entropy or the entropy density as the temperature derivative of F. Right. So the entropy is conjugate to T in that sense, and it counts what the entropy tells you. It counts the number of thermodynamic equilibrium states at temperature beta, in inverse temperature beta, with a given energy. Right, where the energy, the thermodynamic energy, is defined as the variation of the free energy with respect to temperature. And now we're going to do the same thing, but we're going to do this for this parameter m, or rather 1 over m. Okay, so we identify the some free energy or some potential phi, and with the on-shell action, and we compute its 1 over m derivative, and we call that the complexity. So that's an entropy-like quantity, and it counts something very, something very physical. That's not as abstract as the words I just said. So what this complexity counts is just the number of metastable states that characterize this landscape of possible glass states. So yeah, so what happened is that in the high temperature limit, all these values become, in the free energy landscape, the barriers between them become small, and you can freely tunnel between them, and the states are built out of superpositions of all these different values. But as we lower the temperature and we get into this glass states, all the values in this free energy landscape, they become essentially disconnected, or ergodicity between them is lost. So the thermodynamic entropy within each valley is very, very small. That's why the entropy goes to 0. But there's still a large number of these valleys. So there's still a large number of different states. And those are counted by this complexity. Okay, so while the entropy of, the system gets stuck in one of these metastable states, and the entropy there is 0, the thermodynamic entropy, or it's very small. It's not extensive, because there's not much phase space you can explore. But instead, there's this quantity, this complexity quantity that tells you that there's lots of these possible states, and we can compute that complexity using these kind of identities, and we find indeed this behavior, that it is finite at 0 temperature, and it's extensive in n. So it's the thing that takes over instead of the entropy. Okay, I hope that made some sense.
Sorry, what is the parameter m here? Small m.
So small m was this parameter that characterized the Parisi ansatz for the QAB matrix. So QAB was the 2-point function of the spins or the 4-point function of the fermions. And we had to make this replica symmetry breaking ansatz for what the off-diagonal structure of the 2-point function looks like. And in the replica to 0 limit, this is characterized by this function that only depends on these two numbers, m and q.
Is this m related to, say, the frequency or not? Or is totally different thing?
Not directly. No. This is just a parameter that characterizes a property of this state. And the property it characterizes is a little bit, it's a little bit unintuitive because it has to do with the structure of replica symmetry breaking. So replica symmetry is broken, and the particular way in which it is broken is characterized by this function.
Okay.
And that function is basically just two numbers, the Edwards-Adelson order parameter and this m. Okay. You can, how do you get this function? You can think of it as just extremizing the free energy and asking what's the optimal value for this function.
Okay, that's good. And when this q of x goes to 0, it means that we have a ferromagnetic or an anti-ferromagnet, right?
So this x
right,
is between 0 and 1.
Goes to 0. Q of x goes to q is the disorder parameter or the order parameter.
Or if the whole function is just 0 everywhere, that would be like, then replica symmetry is unbroken. We're basically in a, in the spin liquid phase.
Okay.
But this q of x being non-zero tells you that replica symmetry is broken, and we have a long time limit for 2-point functions and so on.
Okay. Thanks.
Good. So this complexity is an interesting quantity. It's kind of like an entropy, but different. It's like an entropy in this ensemble where m is like a thermodynamic parameter that characterizes an important property of the state. Okay, so let me say a little bit about some of the ideas we have about how you could think about these quantities in the context of holography. And we haven't really worked this out. This is mostly a suggestion. But there are some properties of ADS2 that are very reminiscent of what I just told you. So a well-known solution or a well-known way to get ADS2 is to take 4D extremal Reissner-Nordström black holes, Einstein-Maxwell theory, and then there are these Reissner-Nordström black hole solutions. And in particular, there are solutions with multiple horizons. So I wrote them here. They're very simple, very, very nice solutions, which are characterized by this potential V. So V, I wrote the simplest case, but you can add more terms of this form. So this tells you that there are multiple horizons with different charges, Q1 and Q2, and different locations, X1 and X2. And then so these Qi and Xi are free parameters that you can choose. So there's a large space of these solutions. But from far away, so even though you have lots of different solutions of this type, from far away they all look the same. Or so in particular this case here, from far away looks like a single throat with charge Q1 plus Q2. But then as you go close to X1 or X2, you discover that there's actually two ADS2 regions. So as you flow deeper into this geometry, you discover that the ADS2 throat fragments into separate ADS2 regions. And so how do you distinguish these geometries asymptotically? The total charge is not a good quantity, but you can consider something like a dipole moment, the electrostatic dipole or multipole moments. And those will asymptotically tell you the difference between whether you have a single throat or two throats or many throats. yeah, and so that's one feature of this fragmented ADS solution that is reminiscent of the spin glass phase that we discussed. That there's this non-zero average dipole moment that seems to be like this Edwards-Anderson order parameter. And so one way to make this idea more precise would be to quantify in more detail the moduli space of these geometries that locally minimize the free energy, and they're characterized by various parameters that you can choose, like the charges and the locations of the throats. And one could imagine characterizing the size of this moduli space, computing some regularized volume of it, and ask if that is related to the complexity that I described, which also describes the fact that there's many different disconnected states between, but ergodicity between them is broken, but all of these states are important to characterize the system and the fact that the system is complex. Okay, this comment here about the marginal operator, I should discuss the next section first before that makes more sense. So this would be like a very simple picture for how to model this glass phase, and it's of course motivated by this previous work by these authors down here who discussed higher dimensional, more complicated multi-central solutions. But the hope here is that maybe we can, in this ADS2 context, maybe there's a simple way to think about all this. All right, so I'm almost out of time, so I'm gonna do it. So, okay, let me just tell you what this model is. Okay, so various string theory constructions motivate you to write down a different model. And that model is going to look like this. Okay, so I'll just tell you what this other model is that we studied with Tarek earlier this year, and then I'll skip to the last to one property of this model, which I haven't discussed yet. So the model consists of the degrees of freedom are now bosonic rotors. These sigma i's are bosonic spins that parameterize a high-dimensional sphere. So this is a spherical sigma model, and the fact that they live on a sphere is implemented by this spherical constraint, the sigma I squared to n, implemented by some Lagrange multiplier we call z here. I allow for interactions between p of these at the same time, and these are bosonic, so the kinetic term now has two derivatives. So the only, well, the upshot is going to be that this model again exhibits a glass phase with similar properties as what I discussed. Some things are a little simpler, some things are a bit more complicated because this is now genuinely a bosonic model, so some details are different, but okay. But at a most broad brush level, that you see that this model has two parameters. The phase diagram is going to be a two-dimensional diagram. So there's beta j, which is the strength, the temperature in units of j, and then there's also mj, where m is the normalization of the kinetic term. And this was, you could have done that in SYK, but then this normalization you could have absorbed it into the field redefinition. But because we have this additional constraint here, you cannot do that anymore. So the coefficient of the kinetic term is actually a second parameter. All right, so we have two parameters, and beta j characterizes the strength of thermal fluctuations, and mj characterizes the strength of quantum fluctuations. So in this model, we can study the interplay between thermal and quantum fluctuations, and how you get into the spin glass depending on the value of these various parameters. And roughly speaking, of course, you expect for this freezing spin glass phase, you expect that both types of fluctuations should be small, right? If either thermal or quantum fluctuations are too large, then the system is going to leave the spin glass phase. Yeah, so the phase diagram looks something like this. On this axis, there's beta j, and on that axis, there's mj. And there's a corner down here where you have a spin glass. And everything out there, and this plateau value, you don't. You're in a paramagnetic phase here. Okay, so the only thing I'll discuss very briefly is the out-of-time order correlator, because I haven't talked about that yet. So in this model, we computed the out-of-time order 4-point function for these bosonic rotors, sigma I. Yeah, I'm skipping the review. I hope all of you have heard about what this quantity and what it measures. So we can compute that in this model, and it's computed by ladder diagrams like in SYK. We can solve it analytically in some limit. So in some limit, this whole finding the Lyapunov exponent reduces to a Schrödinger problem with a Purcell-Teller potential. So it's a very nice thing that you can do this analytically. But let me only discuss like the final result. If you just compute the Lyapunov exponent numerically. Okay, so again we have two parameters, beta j, that's the color of the curve, and that tells you how strong are the thermal fluctuations, how large is the temperature. And on the x-axis I have mj, which tells you how strong are the quantum fluctuations. And I'm plotting on the y-axis the Lyapunov exponents in units of the maximal exponent. Okay, so what you have here in the left corner, to the left of this dotted jump, is the spin glass regime. So down here, the parameters are such that the system is in a spin glass, and you can see that the Lyapunov exponent, it first seems to jump a little bit, and then ultimately it goes to 0. So as all the fluctuations become very small, the Lyapunov exponent goes to 0, but it has some finite and non-trivial values for small finite temperatures. So some modes still scramble efficiently, and you can see how how chaoticity or ergodicity is lost gradually as you're already in the spin glass, but now you're slowly going to 0 temperature, and you gradually lose more and more of this Lyapunov exponent of chaos characterized by the 4-point function. And then you can also see some interesting behavior at larger values of 1/mj. So for instance, if you sit on one of these curves, means you fix the temperature, and then you just vary the x-axis. So you just vary the strength of quantum fluctuations. You can see that above the spin glass phase, in this paramagnetic phase, the Lyapunov exponent has some interesting behavior. So it's not monotonic, but there's some peak value. So there's a competition between there's some tuning going on, and there's some optimal value for the strength of the quantum fluctuations, where you get the largest Lyapunov exponent at any given temperature. So that's some interesting physics that happens outside the glass phase. All right, so I should wrap up. So here's just again my summary slide. I told you about these two models, mostly about the one at the left, which is in the large M limit, very closely related to the complex SYK model, and which has this interesting feature that spin glass order is weak. So it comes in as a 1/m effect at large M. So we can study this spin glass order perturbatively and therefore analytically, and we can understand a lot of the features analytically. So how this transition happens from this deconfined phase of the U1 gauge symmetry that we had in this Fermionic representation of this SYK type spin liquid to the confined spin glass that we see at low temperatures, where we have these long time 2-point functions and so on. This Edwards-Anderson order parameter. And so we're thinking about how to think about that in terms of ADS2, and we believe that ADS2 fragmentation should be part of the story because it has many of the many similar features. Okay, I'll stop. Thank you.
Thanks a lot, Felix, for the very nice talk. I think we can still take some questions. Yeah, maybe I can start. I have several questions. The first question is that for these quantum fluctuations, like how can I think of a quantum fluctuation on the spin glass state? Like, what does that mean?
Well, it's just so it's a quantum system in the sense that, you know, we're doing a path integral.
Yeah, and the randomness of the coupling.
And the randomness of the couplings. And this M parameter, or its dimensionless avatar, tells you, you know, it's the strength of the kinetic term. Yeah, so let's see. Let me see if I get that right. So if you send M to infinity, that's like a classical limit, I think. Yeah, so you make this kinetic term infinitely dominant.
Mm-hmm.
Yeah, I think that's kind of the intuition.
So here, I feel like probably we take M to be small, or we take it to be big.
This capital M?
Yeah, this capital M.
So it could be, well, it could be anything. So here, so this is the phase diagram that we get by solving the system numerically.
Mm-hmm.
And this axis here, this Y kind of axis, is 1 over M. So you can see that for small m, you go off to infinity here towards the top.
Mm-hmm.
So there the system becomes is very much in this paramagnetic phase. So the spin glass transition happens here, where this, you know, this obvious line
large.
For large m, yeah. But not too large. You know, it's still some finite value with some.
I see.
As you make m very large, you get to the bottom of this diagram. The region where we can solve this model analytically in some nice way is kind of down here, this bottom left corner, where m is large and the temperature is low. Mm-hmm. There we have a lot of analytical control.
Okay, I see. Is this m also related to the SUM group?
There's no SUM here.
Okay, it's a different theory.
Yeah, maybe I should call it something else.
I see. Can you also comment a little bit more about the phase transition in the gravitational part, like which part will correspond to the spin glass state and which part is corresponding to the spin liquid state?
So I think in the the spin glass state would be one where this fragmentation instability occurs. So where the ADS2 throat fragments into many throats, whereas the SYK spin liquid type phase is the one we understand very well. There's no fragmentation. There's just an ADS2, and of course there's a Schwarzian, which one should incorporate into this. You know, we understand a lot more about ADS2 since since the Maldassena-Michelson Strominger paper, so one should include some of these insights and then generalize it to this context.
I see. Spin liquid is more like an effective way of describing that you didn't see the fragmentation. You'd only see the total charges of the black hole.
Yeah, right. So there's no, fragmentation doesn't.
I see.
Okay.
Whom else would like to ask a question?
Yeah, sorry, I hope it was not too far from what people are thinking about.
Maybe it's too clear that people think it's perfect.
I mean, the future task is to work out this picture, you know, and then really connect it to holography in more detail.
Yeah, that sounds interesting. But the things that I feel for example, in ADS2 and the SYK correspondence, it always looks to me that we only know the low energy spectrum on the, say, CFT or the SYK, like the Schwarzschild is due to the low energy spectrum of SYK, right? We even don't know the full duality in ADS2 SYK model, but maybe here, like the proposal, you're going to make it still in the low energy spectrum or something like that.
Yeah, we can study the low energy or the strong coupling regime. You know, where we have these SYK equations and just consider, yeah, up here, and just consider perturbation theory around these equations, roughly speaking, where you consider 1 over m effects, and then see how this picture changes. We don't need a completely microscopic understanding of the duality to make interesting connections, I think.
Yeah, that looks interesting. Yeah, I think that's probably good for today. So let's thank Felix again for the interesting talk, and hope you can report in the future about the progress in the holographic understanding.
Right. Okay. Well,